I think we're ready now. I'm going to go through a quick, simple problem to contrast what's going on when we work with a population and what's going on when we work with a sample distribution. Okay, so we're going to take a look at a situation where we know that the average grade point average for all CUNY undergrads is 2.81. We measured it how many students are part of CUNY? Like 50,000 or something, right? Between Queens College and Brooklyn and so on and so forth. There's like 50,000 or maybe even more students. So we know we know the grade point average for every one of them. We took the average for this entire population. It's a population, right? Not a sample. And the average for the entire population was 2.81. I was generous. I don't know if it's that much or not, right? Undergraduate grade point averages tend to be lower than graduate school for some reason, right? I mean, everybody in graduate school seems to assume they're going to get an A in every course, but that's just the way it is, right? You've been undergraduate, so you know you've experienced this. So at any rate, so the grade point average for all of these students is 2.81, the average for the entire population. And the standard deviation, the variability of these grade point averages is 0.32 grade point averages, grade points. Okay, so if I were to ask you what percentage of students are likely to have within this population a grade point average above 3.0, okay, so how would we figure that out? Well, I'm assuming to start out with that this is a normal distribution. Like, in other words, it isn't skewed in one direction or the other significantly, and there aren't a lot of students with really low grades or a lot of students with really high grades and so on and so forth. But it's pretty much normally distributed. Most people are close to this mean or somewhere close to this mean. Okay, so how would I figure that out? It's a normal distribution. I would be able, I understand from the way normal distribution works that if it's a whole number of standard deviations below the mean or above the mean, I can think about using the empirical formula, right? Just get a rough idea of what these percentages might be that represent the area or the percentage of a population. But in this case, it really is, it doesn't look like it really is close to that. So I'm going to have to do something else, which is I'm going to have to look up in a table or a calculator of some kind what percentage is represented by a grade point average above 3.0. What percentage is represented by a grade point average below 2.0? How many of you guys like using the table, the Z table versus Excel? How many of you guys prefer to use Excel? Oh, most of you guys like to use Excel. Okay, I'm going to do it both ways for the first one, but then I'm just going to stick to Excel since most people seem to like to use Excel. So let's look up the table, and I am recording, so that's a good thing. I actually have it in the folder on Blackboard. Grusty Z table. Here we go. There's a copy of it right here, I think. I hope. Nope, I was wrong. Opened up in something called Text Wrangler. I didn't even know I had that on my computer. Let me open it here. Okay, so here's our Z table. Well, first of all, we have to figure out what Z score is represented by a grade point average of 3.0. Okay, so let's sketch this out. I like sketching it out. Makes it harder to make a mistake. Okay, so here's our distribution. Bell-shaped curve. Our mean was I buried it. Anybody remember what it was? It was 2.81, was it? Should we go back and look? 2.81, and what was the standard deviation? 0.32? 0.32. Okay, and we're interested in what percentage of students had a grade point average in this population above 3.0. Okay, so we need to figure out what the Z-score that represents this value 3.0 is. So Z is going to be equal to the value we're interested in, which in this case is 3.0, minus mu over the standard deviation. Notice I'm using the Greek letters because we're dealing with parameters here, population mean, population standard deviation. So Z, in this case, is equal to 3.0 minus 2.81 over 0.32. Okay, so let's figure that out. And if anybody gets it done ahead of me, they can shout out loudly the answer so I can hear it. But in the meantime, if I get it done first, I'll use my answer. Minus 3.1, oops, 3.0, I'm sorry, where was I? 3.0 minus 2.81 equals that, divide that by 0.32. Okay, and I get 0.59 is my z-score. Okay, and you guys will be good enough to tell me if I'm wrong, right? You're not going to let me go ahead and like do 9 calculations based on that without letting me know. Okay, so the z-score is 0.9. So if I go to my table and I look for, since it's the right of the mean, it's bigger than the mean, it's going to be on my second table, which is positive z-scores. So 0.5, 0.50 is the first column, 0.51, 2, 3, 4, 5, and so on. And 0.59 is 72.24%, 0.7224. Okay, and that area is represented from a z-score of 0.59 down. So in other words, that's the percentage of students that have a z-score that have a grade point average below 3.0, not above 3.0, which is what we were asked for. 0.7, what was it again? 0.59, 0.7224. Okay, so this area from here down is 0.7224. So we're working with this area in here. Okay, and well, let's see, we're interested in this area here, right? So we just simply subtract that percentage from 1. And I'm going to call this 0.772, 6,771, 0.27. That'll look right. 27.76 or 0.2776. About 28% of the students have a grade point average above 3.0. Okay, so next question, next part. What percentage of students have a grade point average below 2.5? Well, we're going to do the same thing, right? Except this time, let me find it. This time, we're going to be to the right side of the mean. It's going to be a negative z-score, and that's going to be 2.5. So let's see. It's going to be equal to, z is going to be equal to 2.5 minus 2.81 over 0.32. Let's see what we wind up getting. Okay, I'm hoping you guys are doing this along with me. Okay, and that's going to be equal to, clear that, 2.5 minus 2.81 is divided by 0.32. Well, we were dangerously close to using the empirical formula there, weren't we? So that comes out to be a z-score of negative 0.97. I'm only going to remember those numbers because we only have 3 digits, 0.97, that we're going to be able to look up on our table anyway. Not so with Excel though. Okay, so negative 0.9, was it 7 or 6? 7. Okay, negative 0.97, which is going to be, there it is, that's column 0.9, it's going to be 0.1660. Right, so this area in here is going to be 0.1660, a little less than 17%. Question was, what percentage of students have a grade point average below that? So that's our answer, right? That's exactly what we needed as it happens in this case. Okay, and the next question is, this is 16.1660, and this area up here is 0.277276 in here, right? Yes? Sure.
0.25 minus 0.281, right?
Yep.
Is that 0.31 over 0.32?
Yes.
That calculation?
Yep, point,
And how do you, like, what's the,
it was point, what was it, 0.9? I forget what we got. Negative 0.96. Right, it's a little less than 1, right? 0.31 over 0.32 is a little less than 1. It's negative because we're on the left side. Okay? And that's what we use to find the z-score, right? And then we were asked for the area below that. So we know we go to that the first table, which is the negative z-scores, and we know from that point down, that's the area, and that's the one we're looking for. So next question is, what percentage of students have a cumulative average between 2.5 and 3.0, right? So there, what we're looking for is the area in between these two. And since we know that this one is 0.1660, and this area above is 0.2776, I think it is, right? If I add those together, they account for 1, 13, 4, 1, 4. They represent about 44% of the distribution, right? 0.4436. So the remaining area, which is in between them, in other words, this is the area we counted for. What we're interested in is the percentage of students that are between 2.5 and 3.0. So we're just going to simply subtract that from 1.4436. And that's going to be, what's that going to be, 6.4 and 5 and 5.5564, about 55%, right? It's going to be the percentage of students between these two values, right? Had I used Excel for that instead, what function would I have used to convert the z-score into an area? Okay. Anybody remember? Equals norm S dist, right? Put in the first parentheses. It's asking me for a z-score. Well, let's say z-score was 0.9. 0.97, I think it was 0.9. What was it again? I don't remember. 0.97. What was that? I'm sorry. I think it was 0.9 something, wasn't it? For the second one, for less than 2.3, 0.31 over 0.32. Might still be here. 0.97. Yeah, 0.97. Actually, I can put in that whole number, right? In fact, I can copy that, I think, and I can go in here and paste that in here, that number, and close the parentheses. Negative 0.960. And I hit enter. Oops, it didn't like that. I think I got an extra period in there. Hang on a second. There we go. That should work now. And I get my 16.64. Okay, so I could do it with Excel. I could do it with the table. Now, there is a little trick in Excel. There's another function called norm dist, parentheses, where I can avoid having to go to the Z table to find a percentage, because it only wants to know what's the value I'm interested in. That was 2.5, comma, what was the mean, 3.0, comma, what was the standard deviation, 0.32, comma, and I'm going to always answer true to this particular version of this. In order to get the whole average from that point down, hit enter, and it gives, whoops, and it gives me, oops, I made a mistake there. 2.5, 0.32, 2.5 is X, 3.0 is, oh, I know what I did there. I think that's a comma. Should be 3.0. That was a typo. Nope, maybe not. Let me try this again. Equals norm dist, parentheses, 2.5, comma, 3.0, comma, 0.32, comma, and true. What did I do again? What am I doing wrong here? Oh, sorry. There you go. Yeah, you're exactly right. Thank you very much. I had 3 plastered in my head. 2.81, comma, there we go. Well, again, I still didn't get it right. 2.5, 2.8, let me start from scratch. Norm, dist, parentheses, 2.5. Well, no, the x is 2.5, right? The mean is 2.81, right? Comma, 0.32 is the standard deviation, comma, true. Now, cross your fingers. I don't have to do this again. It came out right that time, fortunately. Okay? All right, so you can use, now notice that norm dist is kind of a shortcut. We didn't calculate the z-score. It gave us the area without having to calculate the z-score. Norm inverse, you have to give it the z-score. Norm dist, you can give it x, the value you're interested in, the mean, the standard deviation, and it will calculate the area for you. Okay, so let's go back now, see what we had next. Okay, so what percentage of students likely have a grade point average between 2.5 and 3.0? Well, we decided that that was a little less than 56% of students, right? Next question is, what's the probability of randomly selecting one student with a grade point average between 2.5 and 3.0? Isn't that what we just did? In other words, if 55% of the students have a grade point average between 2.5 and 3.0, if I randomly select one person, there's a 55% chance that they're going to have something in that range. So I can look at that normal distribution as a probability distribution. And I can also kind of, keep in the back of my mind that it represents a population, real people with real scores. Okay, so that's really the same answer there. Okay, if you repeatedly, now let's take in the real world, we may not have access to all this information. In other words, we may be part of the student union, the faculty doesn't give out this information, it's considered private and so on and so forth. But we want to figure this out, as students, we want to figure out what's the average grade point average. So we're going to do our own survey. We're randomly going to select 25 people from various institutions and community, randomly select from that population. And we're going to find an average of 25 people. And that average is going to have certain properties, right? That average is going to approximate the population of the mean. It's not going to be the same as the population of the mean. And since I don't know what the mean of the population is, and I don't have access to that, I'll never know how close I am to the average for the entire population. However, I know, well, it's a sample. It's 25 people, not a terribly big sample, but at least I have some idea what I can guess at what the population for the mean is, because it's kind of represented. Now, if I took a sample of size 100, I would be more confident that my sample really represented the mean of the population. If I took a sample of 1,000 randomly selected students, I would be much more confident than either one of those, right? So even though it's still 25 is not a minuscule sample, it's something decent, at least anyway, right? So we have some information from it. Now, the thing is that we really need to have a handle on how well we know, based on our sample, how well we know what our approximation of the mean is. In other words, how good of an approximation is it really? So that's going to be a little bit difficult for us since we don't really know what the mean is. So if we understood something about sampling, the way sampling works, it'll help us figure out how close we might be to actually capturing the mean. Okay, so let's take a look at what we can do here, right? Well, as it turns out, we're gonna do a thought experiment. Like Albert Einstein used to do thought experiments where, obviously you can't follow a beam of light in outer space, but you can think about it and think what the behavior might be. We're going to kind of do a thought experiment. We're going to make believe that we repeatedly take a sample of size 25 over and over and over again, thousands of times. Randomly sample 25 students, find the average. Randomly sample another 25 students, take the average. And we're going to take all of those averages and we're going to find that distribution. We're going to put them all together and make a new distribution of just the averages of size 25. As it happens, that new distribution is likely to be normally distributed. In fact, it probably is even more normally distributed than the original population distribution, considering it might have been skewed a little bit. The bigger the sample size is, the even more likely that you can take a population that's not really normally distributed and get a sample distribution which is normally distributed. That's part of central limit theorem. So what do we know about those sample means? Well, since we're taking many, many thousands of them, right? And we know that each one of them is an approximation of the population mean, maybe a good one, maybe not so good one, but it's an approximation. We know based on the normal distribution, we say to ourselves, well, half the time we're going to have a value, a sample mean, when we take a sample of 25 people, half the time it's going to be lower than the population mean, half the time it's going to be higher than the population mean. Once in a blue moon, it's going to be exactly the population mean, right? So half the time it's going to be higher, so half the time it's going to be lower. It's going to be normally distributed, right? So our sample means, our new distribution has the same mean as the population does, right? Now, remember I told you we'll never know what the population mean is? If we did this thousands of times, you pretty much would know what the population mean is from this distribution. But remember, this is just a thought experiment. We really can't go ahead and do that. So instead, we're going to take a look at the properties of this. So one of the properties is that the sample mean is going to be the same as the population mean. Now, the individual samples, though, are going to be not spread out as much as the population values are. In other words, if you have someone that has a 0.5, you're unlikely to get take say 25 people and get everybody in those 25 people having a 4.0 cumulative average or having a 0.5 cumulative average. That would be a really rare occurrence. Most of the time, your sample means are going to be closer to the population mean than the actual spread of the individual grades for every student. And how much is that? What's the difference between the spread of the population, the standard deviation of population, and the standard deviation of your sample distribution? The sample distribution, the standard deviation of the sample distribution is this population standard deviation divided by the square root of the sample size that you have. So now you have a new standard deviation for all these sample means, these repeated sample means, right? It's really describing a new distribution, which is all these sample means, but it's narrower than the population was, narrower in the value of the population by that value. So since the standard deviation of the population is related to the standard deviation of your samples, by taking the standard deviation of the population and dividing it by the square root of your sample size, now you have how much narrower it is. Now remember, the standard deviation of the population, sigma, is on top of that equation. The sample size, the square root of the sample size, is on the bottom of that equation, right? So that means as the sample size gets bigger, right, n gets bigger, what's happening? The bottom of that fraction, that ratio, is getting larger. So the standard deviation of these samples is getting smaller. They're getting tighter and tighter and tighter, right? The spread is getting smaller and smaller and smaller, right? So let's take a look at what that means for us in this case. In this case, we're assuming that we know the population standard deviation is 0.32. You might say to yourself, well, if I don't know what the mean is, how am I going to know what the population mean is? How do I know what the population standard deviation is? Well, for the moment, we're still part of this thought experiment, we're going to assume that we know it, right? There's a little bit of an issue with that we're going to deal with later on, but for right now, we're going to say that we know it. So what percentage, up here we worked with the population. Okay, we took a sample size 25 from the population. What would you expect the average of all of the samples would be? Same as the population, 2.81. What would you expect the standard deviation of the samples would be? Well, we'd expect it to be 0.32 divided by the square root of 5, square root of 25, which is 5. 0.32 over 5, okay, is 0.064. That's going to be our standard deviation for our sample means. Now, it's getting confusing, right? Talking about standard deviation of the sample means and standard deviation of the population, right? So we're going to give this standard deviation for the sample means a new name. We're going to call it the standard error, okay? So the standard error is 0.064. Standard error is just a standard deviation for these sample means. Okay, so let's take a look at how we're going to apply this. Okay, so now I'm gonna move on here, and I'm gonna say instead of a sample size of 25, which is pretty small, let's say we took a sample size of 100, right? N is equal to 100. Well, what's our standard error going to be now? It's going to be 0.32, right? Divided by the square root of 100, which is 10, right? And that's going to be equal to 0.032. That's our standard error. Okay. What's the probability that a single sample, you took one sample of size 100, what's the probability that you would find that that sample mean of 25 people would be above 30, above 3.0? What's the likelihood that that would happen? Well, I got to go back now and calculate that, right? Let's go back here, except this time I'm going to redraw this to show our sample means. Okay, and our sample means, it's going to be narrower, so I'll draw it a little narrower. Okay, our sample means are going to be, they're going to be 2.81, right? That's not going to change, but our standard error is going to be equal to 0.032. Right? How do we calculate that again? That was sigma over the square root of n, right? Which is 0.32 divided by n was 100. This is 10 is equal to 0.032. That's where we got that from. Okay, so what's the probability that we would take a sample of size 100 and get a value, an average for that sample above 3? Okay, let's see what the z-score is now. The z-score is going to be equal to 3.0 minus 2.81 over my new standard deviation, actually standard error, of 0.032. Let's see what we get now. Okay, 3.0 minus 2.81, right, equals this, divided by 0.032. Okay, my z-score is going to be 5.93. Wow, that's not even on my table, is it? Where's my table? My table doesn't even go up that high, right? My table only goes up as high as 3.4, 3.49 actually, right? What just happened here, right? The likelihood where that 3.0 isn't over there. That 3.0 is way out here, right? Only a tiny likelihood that given this same population that we were working with before, that we would take a sample of 100 people and we would get a value for the average of those 100 people as high as 3.0. Why is that happening? Because our sample distribution is much narrower. How about a sample size of 25? What if our sample size was 25? Well, in that case, our standard error would be 0.32 divided by the square root of 25, which would be 5. So 0.332 over 5. Okay, is equal to 0.064. We did that before. So what would that be now? 0.064. So instead of 0.032, it's going to be 0.064. Right, so it's going to be 3.0 minus 2.81 divided by 0.064. So our z-score there is still going to be almost 3. So remember, with 3 standard deviations left and right, only a tiny, like a tenth or so 1% is going to be above that or below that. So really what's happening here is when our population was spread out like this, but our sample distribution now is spread out so that maybe either end here, 3 standard deviations above and below, are going to be like 3.0 and 2.6, somewhere in that range. Like that's where those values would be. So that's typical of what happens when you take repeated samples. But we can make use of this now because this will help us understand how well we really know the population distribution, the population mean. Okay, and how are we going to do that? Well, I'm going to take I have a spreadsheet that I made up. Okay, I'm going to open that up. It's on Blackboard if you want to download it and open it as well, or you can just watch me work with it. Okay, now I'm going to blow this up a little bit. Okay, so these numbers up here, what I did, remember we had that spreadsheet, that table where I had created a randomly distributed numbers from 0 to that with a mean of 50 and a standard deviation of 9 and so on and so forth. I did the same thing here, except the mean is 100, right? And the standard deviation is approximately 3. Approximate. How did I do that? There's a trick using an Excel function. There's two functions combined here. There's a function called norm inverse, right, which gives us a number. Give it a probability. Uh-oh, what happened? There it goes. Okay. Okay, I think I'm mostly back there. Okay. So there is a function norm inverse, which I can put in, and it gives me the probability, it gives me a number that's related to a value that we can define. For instance, compare if the mean is 100, standard deviation is this, what percentage does this value, what percentage of the time would I get this value if I randomly selected something? Well, I can also, instead of putting a number in, I can put in a function called RAND or random in Excel. And what that does is, I'll show you, don't even have to put a number in, rand and parentheses. If I hit enter, it gives me a random number between, you can't see it there because the formatting cells. Let me just add some decimal places to that. Okay, there you go. And if I do it again, okay, hit enter, I get a different value. Gives me a random number between 0 and 1. Okay, and since that's buried inside here, it basically creates, and it's getting multiplied by 100, it basically creates a list of random numbers that are normally distributed with a mean of 100 and a standard deviation of approximately 9. Okay, that's the way that's designed. Okay, so here's the numbers up here. Okay, so the only problem with this is you keep an eye on those numbers. Every time I do something, if I enter a new number or something like that, then that reloads and it gives me a whole set of new numbers there, whole new population. That population is normally distributed. If you don't believe me, in a little while I'll demonstrate that. Okay, so that population is approximately normally distributed. So from this population, in order to keep it static, I'm going to highlight all these numbers. I'm going to say copy. Then I'm going to go down here to this other list of numbers. And I'm going to highlight the same area. And I'm going to paste it in there, except I'm going to go to edit and say paste special. And I'm going to tell it to paste only the values in there. So now only the values are in there, right? Not the formulas that they were created from. If I clicked into any one of these boxes, you would see in that formula line, you would see the actual number, the actual formula that it's based on. Down here, if I click into it, you just see the number. You just see the number itself. A lot of decimal places, but you see the number. Okay, so what did I do then? Okay, what I did then was I said to myself, each row here, I could look at each row here as a random sample of 10 people from this population, right? Because they're randomly, those numbers are generated randomly, so it's kind of a random sample. So I can find the average for each row, which I did here with these green numbers. And I said to myself, there's 10 numbers in each column. I have another 10 sample with 10 randomly selected people from this population. And I can find the average going down as well. So these are also averages for a sample of 12. So how many samples have I taken? I've taken 10 rows, 10 columns. I've taken 20 samples from this population. Okay, so now this population, this number here is the actual mean for that population. Okay, it turns out it's a little over 100. And the standard deviation for that population turns out to be 9.95. So if I know the mean and I know the standard deviation of the population, I can figure out what percentage, I can figure out how, whether or not this mean, I can figure out an interval for this mean that represents 95% likelihood of getting that value if I thought that that was the population mean, if I took that and I thought it was the population mean. And how do I do that? I say to myself, okay, so let's talk about confidence intervals before I go back up there. Okay, so confidence interval. So now I know I have my distribution. I should have prefaced this with this to tell you the truth. Okay, so I know I have my distribution, my sample means, right? So here's my 2.81 in my previous problem. Here's my standard error was equal to, depends on the sample size. I'm going to use 0.64, right? Now, I know that since this is a normal distribution, 95% of the results are between 2 standard deviations below the mean and 2 standard deviations above the mean. So if I add 2 times 0.064, or about 0.13, if I add 0.13 to 2.81, that would be 2.94, and I subtract approximately the same thing. From that would be 0.8, 2.68. 95% of the samples of size 25 would be between, the mean for 95% of the samples between those two would be between 2.68 and 2.92. Okay, 2 standard deviations above, 2 standard deviations below, and this is what my standard deviation of my sample means, or standard error is. Well, there's a little bit of a problem with that, and we mentioned this last week. And the problem is that this really is not 2.5% here and 2.5% here. The empirical formula was just an estimate. That number of standard deviations that represents 95% is really 1.96 standard deviations below the mean to 1.96 standard deviations above the mean. If we have time, I'll go to the table and show you that that's really the case. You can actually see it in the table. So if I want to know what the probability of getting a sample within that range is, I would take my standard deviation, I take my mean, and subtract my standard deviation, my 1.96 times my standard error, and that would give me the range that I would have to get the sample for 95% of the samples. Well, I'm going to look at this another way. I'm going to use this information to help me create what I'm going to call a confidence interval. Okay, and in this case, what I'm going to do is I'm going to say, okay, I'm going to take a sample of size 25, and I'm going to say my sample of size 25. I'm going to call it X bar. I don't call it mu because it's a sample mean. My sample mean is equal to, in this case, I'll say 2.7. And my standard error, which I calculated before, remember sample size is 25. So my sigma is equal to 0.32. My standard error, therefore, comes out to be 0.064. Okay? So I'm going to say to myself, okay, so here's what I think my mean is. But I really can't be sure of what it is, and I'll never know what the population mean is. But I know that 95% of the time, I'll be within 2 standard deviations of the population mean. So I'm going to take a look at this, And I'd say, well, what range represents 95% of the outcomes that would, if this were, assuming that this was the population mean or close to the population mean. So I'm gonna define my confidence interval by saying it's equal to X bar plus or minus 2 standard deviations, 2 standard errors. Okay, actually, I'm going to say, and I want to be more precise, I'm going to say 1.96 times my standard error. So what is it in this case? It's 2.7 plus or minus 1.96 times 0.064. So that's going to give me a range, right? So the bigger my sample size is, the smaller this number is. The smaller, and multiplied by 1.96, the smaller is the number I'm going to add and subtract from 2.7. So the bigger my sample size is, the narrower this interval is going to be. The smaller my sample size is, the bigger the standard error is, right? Instead of if it were 16, you divide 0.32 by 4, right? So this would be a bigger number than a smaller number, and then so your interval would be wider because this number is going to be bigger. Okay, so I'm going to calculate that and try and figure out what my confidence interval is in this case. Okay, so my confidence interval is going to be 1.96 times 0.064. Okay, that's equal to 0.125. Now that number, that 0.125, represents 0.196 times 0.04. So 2.7 plus or minus, what was that number now? That number was 0.125. 0.125, right? I just multiply those two out. Well, I'm going to give that number a new name. I'm going to call that the margin of error. I'm going to add and subtract this margin of error from my 2.7, right? And when I add and subtract it, I wind up with, I'm going to put this into memory and clear this. So it's going to be 2.81 minus the margin of error, which is 2.68. 2.68, comma, and plus the margin of error. .93. So, in other words, I'm 95% certain that the true population mean is going to be between these two numbers. I'm not really, what I'm really saying is that there's a 95% probability that I will have captured the true population mean between these two numbers. That means that sometimes they're going to miss it. Sometimes they're going to take a sample of size 25 as I did here, and the true population mean be outside of this. If I took 20 samples, right? Remember, we're 95% certain we're going to capture it. If I took 20 samples and found the mean of those 20 samples, right? The mean of those 20 samples, calculate a confidence interval. How many of those 20 samples would I miss the population mean? 1 out of 20, right? 95% of the time, 19 out of 20 times, I will capture the population mean. 1 out of 20 times I won't. So let's go back to that spreadsheet I had. Okay. And on my spreadsheet, is the one, yep, there it is. Okay, here's my spreadsheet. And what I did here was I took my mean, here's my mean. I calculated based on the standard deviation for the population. I calculated a confidence interval, 95% confidence interval. Here's the lower end of it. Here's the higher end of it. The mean, the population mean was 100.15. And in this row, I found that the mean for my sample was 99.7 with a confidence interval of 93.5 to 105.8. The true population mean is between those two numbers. So that one worked out for me. The next one, same thing, 95.2, a confidence interval of 89 to 101. It just captured the population mean. A high end, it almost missed it, but it captured it. And what I did was I tested, I had it set up so that when I miss the population mean, when my population mean is not within my confidence interval, it highlights it in red. So I took 10 samples, determined the confidence interval, took another 10 samples on the columns, calculated the confidence interval. And how many times did I miss it? How many red spots did you see there? One. 19 out of 20 times we successfully predicted that our confidence interval, the range for our confidence intervals successfully captured the population mean between the lower end and the higher end. There's a trick I can do now. And that trick is I can say, I'm going to highlight this again. This is a new set of numbers. I'm going to say copy. I'm going to go back down there and I'm going to paste those numbers in here as values, not as formulas, but as values. Paste special. And I'm going to tell it only put the values in there. And when I click OK, it's going to do a whole new set of calculations. Okay, this time I didn't miss it at all. Okay, 20 out of 20 times I got a confidence intervals that had the true population in between them. There's another trick in Excel. I can repeat an operation by hitting on the Mac Command Y and on the PC Control Y. So I'm going to do that, Command Y. Up. This time I missed it once. Right? I'm going to do it again. Up. Didn't miss it at all. This time didn't miss it at all. Missed it once. Missed it twice out of 20 times. Right? So whenever you hear about like clusters, like cancer clusters and stuff like that, keep in mind there's a lot of variability involved in here. Even here, sometimes I'm gonna miss it more than once out of 20. Sometimes I'll miss it less than once out of 20. Right? But overall, I have 95% confidence that I captured the population mean within that range. So what does that mean for us? That means that I can't tell you if I do a sample, for instance, here, this sample, I predicted that the population mean was 103.9. It's really 90, it's really almost 100, right? I predicted it was not 103 based on my sample size of 10. I can't, since I don't know what the true population means, I can never tell you how close I am to the mean. However, I can tell you that within this range, this confidence range, this far below and this far above the mean, this mean that I just calculated, that I'm 95% sure the true population lies. Okay, so let's say I sample 100 New Yorkers and test their cholesterol. Right? Turns out their average cholesterol, total cholesterol was 134. And let's say I sample, I'm going to blow this up a little bit. You can see it. Okay, and let's go even a little higher. Let's say I sample 100 people from Miami and I test their cholesterol. And the average cholesterol for that sample of 135 people is 143. Okay, that's Miami, and this is New York. Whoops. Okay, so can I say people from Miami have a higher cholesterol level than people from New York on average for the entire population? I can't, I don't know because I don't know how, it's only 100 people. I don't know how accurately I know this. However, I do know that, for instance, let's say we have another study where they did a very large survey and they found the variability for cholesterol levels in the human population, and we happen to know the standard deviation for the values of cholesterol. So I can calculate a confidence interval. Let's say that the confidence interval for New York turns out to be 130 to 138. And the confidence interval for Miami turns out to be 140 to let me change that. Turns out to be 135 to, let's see, that's less, 151. 151. Well, what does that tell us? That tells us that we're 95% certain that the average cholesterol level for New Yorkers, the entire population, is between 130 and 138. And the average cholesterol level for people from Miami is between, we're 95% confidence, is between 135 and 151. Can you tell me with much certainty that Miami, that based on this sample, these two samples, that we know that Miami has a different cholesterol level? You can't, right? Because I mean, it could be 135, and New York could be 138. They overlap, don't they? Right? If they didn't overlap, let's say that this was instead of 130, 138, that this was 141 to 145. How do you feel about it now? Whoops, where'd it go? There it is. Right? How do you feel about it now? You're 95% certain that the New York population has average cholesterol level between 130 and 138, and you're 95% sure the Miami population has an average cholesterol between 141 and 145. Well, even though you don't know what the mean is for the population of New York, you don't know for sure what the mean of the population of Miami, you have to feel better about that, right? Because now you're saying to yourself, gee, I have this range in mind for New York with 95% certainty, and this range for the true population mean for Miami. So now, since they don't overlap, I'm feeling a little bit more comfortable, right, about this. We don't really do this. We don't like to use overlap, use the confidence intervals this way. Next week, we're going to learn a different technique, which uses the difference between the two means, and it uses the variability for samples of that size. There are a lot of reasons why you wouldn't use this. A lot of times, for instance, the sample sizes could be different in New York and Miami. There's also mathematical reasons why you wouldn't do this. But certainly you can see how a confidence interval, a narrow confidence interval, gives you more confidence that you know what the population mean is, right? Where a wide confidence interval leaves you a lot of uncertainty of what the population is. And it also leaves you with a little bit of doubt about whether you can say one population is different than another population. Now, let's say I said, for instance, instead, that we knew for sure that the Miami average cholesterol was 140. We tested everybody in Miami, their average cholesterol was 143. How do you feel about that? Well, now we're 95% sure New York is between these two values, and Miami is outside of that range. So we're 95% sure that Miami, the average cholesterol level for New Yorkers is different than people from Miami. Where if this had come out to be 136, we couldn't say that anymore, could we? Everybody comfortable with that? Let's actually work on a couple of examples. And I think if you go to exercise 1, okay, and I'll blow this up just a little bit. And I'm going to get you guys to do this, hopefully. Okay. Oh, no, that's a proportion. I'm going to go to the second part of this. I don't like this one. Actually, why not? St. Patrick's Day. Let's stick with that one. Okay, second part of this. Okay, you go to 40 New York City pubs on St. Patrick's Day and find that they inventory an average of 42 different types of beer. You calculate the standard deviation for these pubs from your study data, and you find that 6.3 beers. So pubs carry an average of 40 beers, and the standard deviation from pub to pub to pub is 6.3 beers. Okay, so you sample, that's 40 different pubs that you got this information from. Is 40 mu or X bar? $40 beers. You run around to is the what? Right. Well, 40 actually is the sample size, right? The real question is 42 mu or X bar, right? Look right there. Okay, so it's X bar, right? It's a sample mean. We didn't sample every pub in New York City. We only sampled 40 of them, random selected 40 and sampled it. So 42 is it's X bar. Is 6.3 sigma or standard deviation? Or standard deviation? Right? It's a standard deviation, right? Because again, it's a sample that we're working with. Okay, so let's calculate. Let's assume that 6.3 is the standard deviation. Oh, I'm sorry. Calculate standard for these pubs in your study. Okay, for 6.3 beers. Let's say that we know that this is the same as the population standard deviation for the moment. Calculate the standard error for repeated samples of this population of size 40. Okay, so we sampled 40 pubs. If we had done it repeatedly, what would be the standard error? So you guys figure that out for me. Standard deviation 6.3 divided by the square root of the sample size. Actually, I should do this back the other way around. I'll do it while you're doing it. 40, that's square root of 40. I'm going to put it into memory, clear it, and I'm going to say 40 divided by, oops, I'm wrong, I got that wrong. What am I going to say? 6.3 divided by equal. Okay, I got a standard error of 1. You guys get the same thing? Okay, good. Okay, now calculate, okay, good. Calculate a 95% confidence interval for the beer inventory at different pubs based on this sample. So how are we going to calculate that? We know what the standard error is. We know what the mean in our sample was. The mean number of types of beer was 42, right? So how are we going to calculate that? I'll put the formula up, right? It's going to be X bar plus or minus 1.96 times our standard error, right? Our standard error was equal to approximately 1, right? How did we get that? We got that from 6.3 divided by the square root of 40, right? Sample size. So what was our mean number of beers that they carried? I think it was 42, right? Okay, plus or minus 1.96 times our standard error, which was equal to 1. Pretty convenient, right? So I'm gonna round this. But actually, I'm not gonna round it. I'm gonna actually calculate that. 42 plus or minus 1.96. What's our 95% confidence interval? I'm going to use Excel to do this. 42 minus 1.96 and 42 plus 1.96. Oops. Okay, so our 95% confidence interval is between 40 and 44, basically, right? So in other words, we think that the true population mean for the number of beers, a number of types of beer that New York City pubs, Irish pubs stock is between 40. We're 95% sure the true mean of number of beers is between 40 and 44 types of beer. Okay, does that mean that there aren't pubs that stock 30 and aren't other pubs that stock 72? Yeah, there are. But we're 95% sure the true mean, that the mean for the entire population of all these pubs, there are probably 1,000 of them in New York, right, is between those two numbers. Okay? All right. So let me ask you something now. What if we wanted, that's 95% certainty, right? What if I wanted to be 99% certain that I captured the confidence interval? That's 40. This is 40 to 44. right? That's my confidence interval. What if I wanted to be, and that's 95% certainty. What if I wanted to be 99% sure, right? What would I need to do to that confidence interval be 99% sure I captured the true population average? I got to make that confidence interval wider, right? Right? If it's 40, if I say 40 to 44, I'm 95% certain. If I had said 38 to 46, am I more certain or less certain that I captured the mean? I'm more certain because I have a wider interval. I have a better chance of capturing the mean, the true population mean, right? Well, how do I go from 42 plus or minus 1.96 times the standard error, which turned out to be 1? How do I make that wider so that I know I have a 99% certainty, right? Well, if I go back to my normal distribution, right? Remember, I could determine a z-score at either end here where 99% of the outcomes are between those two values. That means that this area here is less than 0.5%, 0.00005, and this area here is 0.005. What z-score do I need to accomplish that? Well, let's go take a look at our table. 0.005. Okay, so I'm gonna work with the top table. 0.005. 0.005. Let's see what I can get, how I can get to the closest here. Here we go. Here's 0.0049 right here, right? 0.005, pretty close to 0.0049. It's the closest one I got. What z-score does that represent? Well, that z-score is negative 2.58, right? So instead of using 1.96, while I'm here, let's look at negative 1.96. Negative 1.96 means that area at the bottom of the curve is normal distribution is 2.5%. That's 2.5%. 0.25. 0.025. 2.5%. 2.5% at the low end, 2.5% at the high. 95% is between. 90% outcomes are between 1.96 standard deviations above and below the mean. That's why we use 1.96 instead of 2.0 from the empirical formula, because it's really more accurate. Right? Okay, so what do we need for 99% confidence? That number was 2.56, 2.58 rather, I'm sorry. So now I'm going to say 42. Oops, 42 plus or minus 2.58 times my standard error, which was equal to 1. Right? So what's that going to be? I think I used Excel for that, didn't I? Okay, so instead, I'm going to go in here, and instead of 1.96, now it's going to be 2.58. And 2.58 added. So our new confidence interval is 39.4 to 44.6. 39.4 to 44.6. It's wider, so I'm more confident. This is 99% confident. What about if I'm willing to be only 90% confident? I don't mind being wrong a little bit more. What can I do with my confidence interval? I can make it narrower, right? So if I want to make it narrower, I need to use a z-score, which represents an area where we have 5% below it, 5% above it, and represents the middle 90% of outcomes. I'm not going to bother to go to the table to look it up, but I can tell you that z-score is going to be 1.64. So if I use 1.64 in here, right, this margin of error becomes a smaller number, so I'm adding and subtracting a smaller number, which means my confidence interval is narrower. 90% confident, 99% confident, 90% confidence interval, 95% confidence interval, 99% confidence.